Welcome to Module 1, Physics Applied to Diagnostic Imaging. This is Chapter 2, Section 2. Ultrasound Interactions with Matter. When ultrasound strikes a tissue, it can be reflected, refracted, scattered, or attenuated. Before we start, let us review what is acoustic impedance. Acoustic impedance is the resistance to propagation of sound. It is the product of the density of the tissue and speed of sound. That is Z equals rho times C. What is the point of this equation? It just tells us that because different tissues have different densities, they will have different acoustic impedances. This difference will affect how sound travels from one tissue to another. Now, let us move on to the first interaction. Take a look at this ultrasound image. See here that at this boundary, we have a muscle-fat interface. These two tissues have a different acoustic impedance, but not that much. Hence, almost 100% of sound gets through to the deeper structures. In other words, only about 1% of sound is reflected. Now, think about muscle-air interface. In this case, the acoustic impedance between the two is much more different. Because of this, nearly 100% of sound is reflected. This is the reason why we use a coupling gel, to eliminate the air in between the transducer and the skin, hence reducing the amount of reflected sound. The next interaction is refraction. Take a look at this ultrasound beam, which approaches the margin of the gallbladder. Notice how it is not perpendicular to the boundary. What happened to the beam after it hit the boundary? It changed direction. That is refraction. The change in direction of the ultrasound beam when the beam is not perpendicular to the boundary. In this example, because of refraction, there is creation of an artifact which can be mistaken as a shadow. What about scattering? Scattering means going into different directions. Now take a look at this example. The ultrasound hits the liver parenchyma, which is composed of tissue and cells which act as multiple tiny reflectors. Since the liver here is healthy, the degree to which the ultrasound is scattered in one segment is similar to the nearby segments. This creates a characteristic homogeneous echo texture which helps us localize organs and localize lesions. Now, let's move on to attenuation. To attenuate means to lessen. Hence, in this ultrasound interaction with matter, acoustic energy is lost with distance traveled. It is caused partly by scattering and tissue absorption. The higher the ultrasound frequency, the higher the attenuation of the ultrasound beam. In other words, a 7 MHz linear transducer will have 7 times the amount of attenuation compared to a 1 MHz beam. A 2 MHz curvilinear transducer will only have 2 times the amount of attenuation compared to a 1 MHz beam. So which probe will we use if we need to visualize structures of greater depth? Yes, a curvilinear transducer. That concludes this section on the ultrasound interaction with matter. When ultrasound contacts tissues, it can be reflected, refracted, scattered, or attenuated.